Okay, so it's just after 1 o'clock, so I think we'll kick off. Thank you to everyone for coming along. So it gives me great pleasure to introduce to you today Professor Gordon Hamilton from Lancaster University. And so Gordon is no stranger to the school, although it has changed a little bit. We were just commenting on how much more comfortable the Nuffield is from the time when he was here in the late 1980s as a postdoc.
Not 1880s.
But he did a stint as a postdoc in Liverpool, at the school here, and then moved on for many years through progression of posts, finally ending up with his own chair at Keele University. And about 3 years ago, he moved on to another chair. One chair is never enough. Moved on to another chair at Lancaster University, hooking up there with a couple of other ex-LSTM people to form a kind of critical mass of sandfly expertise in the UK, I think. And that's been a real strong theme of Gordon's research for many years. And what's the reason I was particularly interested in having him over here today, actually, because there's many of us here who are interested in sandflies and leishmaniasis, and I think it's been far too long since Gordon was over here as well. So today Gordon is going to be talking to us about visceral leishmaniasis control in Brazil. So over to you, Gordon. Thank you very much.
Thank you very much. Right, so I have to switch this on.
You do.
Okay. All right, ground control. All right, well, thank you very much for inviting me. It is probably 6 or 7 years since I was last here, and it's nice to see that some things are still the same. Benson's Beds is still across the road, and the tailor shop. So some things stay the same, and some things change. But it is very nice to be back. I feel of Liverpool School of Tropical Medicine because I did my first postdoc after my PhD here, so I have a very fond regard for the institution. So today, when I came here, I started working on sandflies and their pheromones with Richard Ward, who was a member of staff here. He left as a reader to take up a professorship at Keele University, and I kind of went along with him as part of his luggage, you might say. But I've been working then really on sandflies and pheromones since I started at Liverpool School of Tropical Medicine. I was trying to remember, it was 1985 when I first came here, or it could have been 1989, but anyway, it's lost in the mists of time. So what I want to talk about is some of the work that we have been doing or being involved in that was initiated at the Liverpool School of Tropical Medicine, but which I've continued working on over the years. So, visceral leishmaniasis. Let's see. So we could talk a little bit about the transmission cycle of visceral leishmaniasis. In Brazil, it is a disease that involves an intermediate host, particularly domestic dogs. So leishmaniasis in Brazil is caused by Leishmania infantum, which is the European Leishmania that was probably imported by settlers from Europe into Brazil, into South America when European settlers were moving there. It's very unfortunate for Brazil and South America generally that there is a permissive vector, Leucemia longipalpus, a sandfly, that readily was able to transmit the parasite. It's likely that the parasite was taken to Brazil in the dogs that the settlers took with them, as well as their own infection. So in Brazil, the sandfly transmits the parasite between dogs and occasionally to people. For dogs, the disease is always fatal if they catch the disease. And for humans, it can be fatal if it's not treated. And it tends to affect mostly young children, very young children up to the age of 1 or between 0 and 5 years old, probably because their immune systems are not as advanced. But of course, it affects people all through the age spectrum. If it's not treated, as I said, it is fatal, but it can be treated using antimonal drugs, which are rather unpleasant. So the vector is abundant in animal shelters, or it was believed to be abundant in animal shelters, but it's probably far more widespread than that in the environment, and we now have evidence to show that it is. Previously, it was considered that it was mainly associated with chicken sheds, and I think that's probably because the methodology used to investigate the distribution, it was using CDC light traps, which aren't very good at finding the insects in the environment. I might be able to talk about that a bit more later. So in Brazil, dogs are the sole reservoir, humans are incidental hosts, and the vector is abundant in animal sheds. Okay, so in Brazil, there are 3 strands to controlling visceral leishmaniasis. The first is vector control, and this is a reactive insecticide spraying. So when a human case is identified, then the Ministry of Health have a set of procedures that are enacted, and lambda cyhalothrin is sprayed in the house where the human case is found, and in all houses and structures up to 500 meters around that case. So that is reactive response. So they do not go out and spray insecticide unless there is a human case identified. The second strand is reservoir control, and in Brazil that means controlling the dog population. And this is a proactive approach, meaning that the Brazilians go out and they will survey dogs in an area, and if they find that the dog is infected, they will kill the dog. This is hugely controversial in Brazil because it doesn't really work very well. However, if they did it or were able to do it correctly, then it could be successful, and it's been modeled to show that removing infected dogs from the environment would get rid of visceral leishmaniasis. And we'll talk a bit about why it doesn't particularly work in Brazil a bit later. Then the third strand, so I'm going to talk about our work in both of these areas, but the third area recommended by the Ministry of Health in Brazil is the use of therapeutic drugs. These tend to be antimonal based, so it's essentially using toxic chemicals to kill the parasite in situ, in the human. There is no human vaccine, although there's been some substantial amounts of work that have been done. None currently exists. There is a canine vaccine which has some success, but it's expensive and it's not used widely by the Ministry of Health. The antimonal-based drugs are very unpleasant, and if anybody knows of Ben Fogel, how many people know of Ben Fogel? He's a bit a generational thing, perhaps, but hand down. No, never heard of him. He caught Leishmania infection in Peru. It was identified in the UK, and he had 4 weeks of treatment at the London tropical disease hospital, and he said it was the worst experience of his life. So either he's prone to exaggeration or it was pretty bad. So you can imagine a child who is being treated with an antiviral drug, then it's not very pleasant for them. New drugs are expensive and seem to generate resistance more quickly, and I think possibly the Indian experience of development of anti-Leishmanial drugs is indicative in that area. Oh, I didn't know I had that. So there are 68,000 deaths, human deaths in Brazil because of leishmaniasis every year, and there are hundreds of thousands of dog deaths, which is perhaps not very significant, but if you're the dog owner and your dog is taken away and euthanized, people aren't particularly happy about it. And as I said, the dog culling program in Brazil is very, very controversial. Do we have any Brazilians in the audience? One? So you probably could say more about it than me. Okay, but the Ministry of Health in Brazil are very active in trying to control the disease. They take a great deal of interest in it, and they spend huge amounts of money. The unfortunate thing is that it's not been successful. And by 2016, the number of dailies, disability adjusted life years, had increased to around 38,000 per annum, an increase in 120% from 1990, indicating very clearly that the VL control program in Brazil currently is not working. Okay. So, what can we do about it? Well, I'm not sure that this is the answer, but this is my attempt and of my colleagues to provide an alternative solution. So we'll talk a little bit about Leucemia longipalpis and its mating ecology. I have to be very careful. I tend to go on too long. So you have to do this every so often to tell me to hurry up. I think the key to controlling the disease is through vector control. But to do that correctly, you have to understand a little bit about the behavioral ecology of the vector. And really not a great deal of work has been done on it. And these are our observations. But if this is a composite picture showing the kind of environment outside back door of most people's houses in Brazil. So there is a chicken shed. Many people have chicken sheds. About 20% of the population keep chickens. So there's the chicken in the chicken shed. Chicken sheds are very loosely constructed buildings. They have a dog, which can become infected with Leishmania. As I mentioned, it acts as the source of infection for other dogs and for humans. And they may keep other animals, or the neighbors may keep other animals. And all of these other animals and the natural animals in the natural environment all provide blood meal sources for the sandflies, Leucemia longipalpis. But what's happening is that, in particular, chicken sheds act as a focal point for mating activity of Leucemia longipalpis. And what appears to happen is that, for some as yet undetermined reason, a lone male sandfly will arrive in a chicken shed and start producing pheromone early in the evening. And that pheromone then attracts other male sandflies. And eventually, you get sufficiently large numbers of male sandflies that are producing their pheromone, and that attracts female sandflies, which turn up later in the evening. And the females come for the blood meal, and they also come and get mated by the males. The females then disappear off back into the environment, and the males remain throughout the night, lacking, they're forming these aggregations, producing pheromone, and so on. The Ministry of Health, when they find that there is a sandfly, a leishmania problem, a human VL case, they come along and they spray all of the structures, the human dwellings and the chicken sheds and pig pens and all the rest with insecticide. And what happens then is that that stops the aggregations of males from forming, and it stops the females from coming to those aggregation sites. So in effect, although they may well kill all of the sandflies in the chicken shed on that night, it stops the sandflies coming back to that site on the next night, because that first individual male doesn't arrive and doesn't, or if he does, he's killed, so he doesn't produce pheromone, so more males don't arrive. And sandflies are actually very loyal to their aggregation sites. They keep coming back night after night after night. So if you disrupt this mating ecology by spraying insecticide, then in effect what you're doing is moving the problem to untreated sites where insecticide hasn't been produced. So our solution to the problem is to replicate this aggregation of males by using synthetic pheromone. So we can make the pheromone, I'll explain a bit more about that in a minute, put it in the chicken shed that's been sprayed with insecticide, and the sandflies keep coming back to the same place night after night and getting killed. But the pheromone is still being released. Okay, so the pheromone is produced by male Lutzemia longipalpus. It's produced from glands in the abdomen. One of the issues about Lutzemia longipalpus is a species complex producing, and members of the complex produce at least 4 different types of pheromone. The one that we've been working on is this one. It's called 9-methyl-germacrine B, and it's produced most widespreadly in South America and in Brazil. And each male releases about 150 to 260 nanograms per day. And what we were able to show was that a plant called Geranium macrorhizum produces a chemical that's very similar to this compound, and you can transform that chemical using synthetic chemistry to this pheromone. And you can make in small batches up to 10 grams, which represents the amount of pheromone that produced and released by 38 to 66 million male sandflies, which represents a lot of pheromone. And so I'm really squeezing in about 10 years of research into this slide. But that pheromone, then the synthetic pheromone, can be repackaged in a little polythene sachet, and that releases the pheromone slowly over a period of time. And we can make these lures, we call them lures because they attract male and female sandflies, for about 90 days in the field. So if we put one of these lures in our chicken shed that's been treated with insecticide, then that chicken shed can be attractive to male sandflies and female sandflies for up to 90 days, 3 months. It does depend a little bit on the temperature during the day. So obviously the hotter it is, the more quickly the pheromone is released. But we know that it works for up to 90 days. So we did some experiments in the field. where we used CDC light traps with no light for 2 nights in experimental chicken sheds, and then added insecticide and pheromone. So we sprayed with lambda cyhalothrin and added the pheromone and trapped for 2 nights to see what happened. Our control was chicken sheds where we didn't have any pheromone at all. Okay. So 2 days, and then we counted the numbers of females and males. Then we put in our intervention, which was the pheromone and insecticide, or the insecticide alone. And then we counted the numbers of males and females after that. What we found was, before the intervention, after we had applied the insecticide, that the number of females decreased. So, as we expected, the insecticide is killing the female sandflies, and we got a nearly significant decrease after 2 nights. But when we had the pheromone, we had a very significant increase in the number of female sandflies that we were catching in the pheromone insecticide treated chicken sheds. And the same thing was also true, same pattern for males. We had a decrease in the number of males that were trapped when there was no pheromone, just insecticide. And then after the pheromone was added, then we got a significant increase in the number of male sandflies. So kind of, that's the evidence that when the Ministry of Health comes along and sprays the insecticide into chicken sheds and around houses, that really what they're doing is they're killing the sandflies that are there, but they're stopping the recruitment of insects to those treated sites, and that the pheromone can overcome that lethal effect of the insecticide. And that was the basis then of the lure and kill approach that we then promoted to the Wellcome Trust, so that they gave us money to do a stratified cluster randomized trial in Brazil to see what the effect of that control method might be. So what we wanted to do was to determine if the sandfly synthetic sex aggregation pheromone co-located with insecticide reduced canine Leishmania infantum infection incidence. So I don't think I'll go through all of that, because that's our study design and structure, which the Wellcome Trust were very interested to see beforehand. And this is essentially what we did. We had been working in a different part of Brazil, but this area of Brazil in Araçatuba, which is the western part of São Paulo state, there was a particularly high incidence of canine visceral leishmaniasis. Over 50% of the dogs have antibodies to VL. And what we did was we divided 42 clusters, which represented by municipalities or parts of municipalities in Araçatuba city. We divided it into 3 arms. The first arm received the synthetic pheromone and insecticide, and that treatment was replaced every 3 months. The second arm, the dogs were treated with insecticide impregnated dog collars. And insecticide-treated dog collars were produced by a company called Scalibor. I don't know, some of you might have heard of Bob Killick-Kendrick. He did some work some years ago showing that these insecticide-treated dog collars were very effective at killing sandflies on dogs. So that was our, if you like, our positive control, because we already knew that insecticide-treated dog collars are very good at killing sandflies. The problem for the Ministry of Health in Brazil and for local people is they're quite expensive. So in one sense, although they could potentially reduce canine visceral leishmaniasis incidence, they're not widely used. And actually, there is no study that shows how effective they might be. And the third arm of our trial was a placebo control, so there's no treatment whatsoever. So we tested 4,918 dogs. This with colleagues, Oren Courtenay at Warwick University. We tested these dogs for VL infection. We recruited 2,971 dogs into the trial, and then we followed up at different times during the trial 1,400 dogs to see what their infection status was. So we recruited negative dogs, and then we wanted to see how many of those dogs became infected during the trial period. So this is just a map of our study site, 150 kilometers from east to west, 75 kilometers from north to south. These are all of the municipalities, and they are distributed either as control, collar, or pheromone arms. And then this is within the city of Arasatuba itself. It has a population of about 350,000 people. So there's plenty of opportunity within the city to divide it up into different treatment arms. But as you will see, the Arasatuba, the city itself, there's something very strange happening there. Okay, so our trial outcomes, what were we interested in measuring? Cluster level cumulative seroconversion incidence in naive dogs. So what we're interested in wasn't just was an individual dog protected, but was the community of dogs protected by our intervention. Because the dog collar gives a personal protection for an individual dog, but it was not clear either if it also provides community level protection. And clearly for the Ministry of Health, what they would be most interested in is a community level protection of their intervention. So not everybody necessarily has to have the treatment, but if a proportion of the population of dogs have this treatment or houses, does the population as a whole get protected? We wanted to know what the parasitological outcomes might be in terms of parasite loads confirmed by qPCR, and the relative changes in cluster level household counts of Longipalpus. So are we also having an effect on the vector and the numbers of insects, Longipalpus present around houses? Okay, so what did we find? So what we found is if we grouped all of the strata together, 1, 2, and 3, so the strata was whether there was high infection, medium levels of infection, or low levels of infection, VL infection, in each of our arms. What we found was that we did not get a significant decrease in seroconversion incidence. So dogs were not generating antibodies to Leishmania infantum more significantly if you looked across all 3 arms, depending on the arm. But if you looked at strata 1 and 2, which were the strata outside Arasatuba, then we did get a significant decrease in seroconversion incidence, so that the dogs were being protected. The collar was very much more significantly protective than the pheromone. And then we were also interested in infection incidence and tissue parasite loads. So what we found was that in the pheromone arm, compared to the control arm, we had a very significant decrease in parasite incidence whenever we used pheromone and insecticide. And the parasite load was decreased. And it was actually more significant than using dog collars. Okay, so that seemed very promising. The summary of the results then, the pheromone and insecticide intervention provided approximately 13% protection against anti-leishmania antibody seroconversion, indicating a protective effect, 52% reduction in parasite infection. Parasite loads were reduced by 53%, and the number of sandflies in households was reduced by 49%. So it's a kind of a mixed pattern of results. It looks like that the pheromone does have a protective effect for the community whenever the pheromone is being used in the smaller municipalities outside Aracatuba itself, but not whenever we included Aracatuba in some of the calculations. The impregnated collars is an interesting comparison because, as I said, impregnated collars are used by the Ministry of Health in some cities as almost as a gold standard for protecting dogs. Although they gave higher than the pheromone, 36% protection against anti-leishmania antibody seroconversion, we only had a 23% reduction in parasite infection compared to 52%. Parasite loads were reduced by roughly similar amounts, and it had a slightly smaller effect on sandfly abundance. So the dog collar, the use of dog collars and the use of pheromone and insecticide seem broadly similar, if I could put it that way. Okay, so what should we do about this? Well, one thing is that in our trial, we were only able to treat about 20% of the households in the municipalities with the insecticide and pheromone, because we were tied to putting the insecticide and pheromone in chicken sheds, and only approximately 20% of the houses have chicken coops. So what we would really like to do is increase the coverage to 100%. So in an area where there's high transmission, we would give every single house pheromone and insecticide. And what we have found since this work was done is that Longipalpus are in fact very much more widely distributed in the environment than the chicken shed model indicates. So if you use the pheromone in places where there are no chicken sheds and no dogs, you still trap large numbers of Leucemia longipalpus. So potentially every single house could have insecticide and pheromone. We could make the pheromone lures last longer by increasing the amount of pheromone that we put into them. So at the moment we put 10 milligrams of pheromone. That lasts for up to 3 months. If we put 20 milligrams of pheromone, then that could last longer. We don't know how long because we've not done it. Instead of using spraying residual insecticide, we could use insecticide-treated netting to deliver the insecticide dose. And we have tried some experiments with this, and it looks promising that instead of having to spray insecticide, we just put out a 1 or 2 square meter piece of insecticide to kill the sandflies. Quite a problem is the commercial synthesis and manufacture up to now we haven't really had any evidence that the pheromone would work. Now that we have the evidence that potentially the pheromone will work, we can approach synthetic companies who can manufacture the pheromone and in bulk, which we've not been able to do up to now. The drawbacks are that the synthesis is difficult to do, and it will make the pheromone expensive on a per gram basis. But as you saw, that 1 gram of pheromone produces a lot of attractiveness, if you like, for male and female sandflies. But that it will be a problem. The synthesis route is also challenging, and that is why it is expensive. The pheromone is only really applicable, the one that we have worked with, for one of the members of the species complex. And there is one other really important, in terms of its distribution, pheromone type, which we will have to address for that pheromone, that particular group of sandflies. And I think it's going to be even more challenging than the synthesis that we have done up to now. Okay, so that's the pheromones out of the way. That's where we're up to, really, a very potted history, if you like. I mentioned that the second part of the Ministry of Health's approach to dealing with visceral leishmaniasis is the elimination of dogs that are infected with VL, and for numbers of reasons that's not been particularly successful. So we've been using a cheromonal approach as opposed to pheromonal. Pheromones are chemicals that are produced by organisms, not the insect, that are attractive to sandflies. So for example, we all produce chemicals, it's our smells, and sandflies and mosquitoes are attracted to those chemicals, and we all know that some people are more attractive than others to biting insects, and it's likely that their chemicals are responsible for that. What we are particularly interested in is that the cheromones, those volatile chemicals that are produced by dogs. And we know from work that's been done by our own group in the past that an animal, when it's infected with Leishmania infantum, the odor changes and it becomes more attractive to the sandfly. And so what we wanted to know was, could we, and so other people have also been working in this area, and some Brazilians a few years ago showed that the odor of dogs infected with visceral leishmaniasis, they could detect differences between infected and uninfected dogs using mass spectrometry. The problem, and that's all very good, but the problem is you can't use mass spectrometry as a diagnostic tool in the field because a mass spectrometer is very expensive. It requires specialist analysts to use it, and it wouldn't necessarily replace the problems that occur with the current available diagnostic techniques. So what we are interested in knowing is, could we use the cheromones as a diagnostic tool? So in Brazil, identification of dogs infected with visceral leishmaniasis follows a two-stage serodiagnostic protocol recommended by the Ministry of Health. So there's initial screening using a immunochromatography diagnostic test, a DPP CVL test. And if that is positive, the theory is that the dog, then the blood is checked using ELISA in a lab, a remote lab, and that is a test that can take 2 weeks or longer. The problem with that is, of course, that the dog that is suspected of being infected isn't removed from the population, and it is then capable of transmitting to sandflies. this diagnostic protocol should work, and it's been modeled to show that it should work, especially in areas of low to medium transmission, but it doesn't. Partly because of the lack of facilities to collect and euthanize dogs, and all of the kind of the infrastructure around that. And what's happening is that the dogs are being diagnosed on the basis of the DPP test alone. And often the dog is only really identified as potential for DPP testing based on how it appears, how it looks to the people who are the Ministry of Health when they come to visit your house. So if your dog looks fine, it doesn't get the DPP test, but the problem there is the dog can look fine but still be infected, and it can still be infectious. So that doesn't necessarily identify the dog. There's a lack of, and this is quite a significant issue, a lack of public confidence in the outcomes of all of this testing. So people who love their dogs in the way that we love our dogs in the UK, and though they hide the dog when the Ministry of Health comes along to look at it. Say, my dog is fine, or I don't have a dog. What dog? What's that dog bowl? That's the neighbour's dog. Okay, so, and the people know that the testing, the DPP test, is not accurate. And so they know that they have a lack of confidence. So this is what a DPP test looks like. It's a little sample of blood goes into this reservoir, and if you get two lines, then that indicates that the dog should have the confirmatory test, but often the local veterinarians decide that the dog should be euthanized at that point. Okay. So the problem seems to be the delay in the second confirmatory test, and perhaps an over-reliance on the DPP test, which is, has some accuracy problems. Let's put it that way. So we know that there is a difference between infected and uninfected individual dogs in their smells. We know from previous work that parasites can manipulate host odors, so it's not necessarily very surprising. And Oliveira in 2008 showed that there were differences in the chemicals that infected and uninfected dogs produced. And the change in smell of the dogs, so what that essentially says is that the dogs that are infected smell differently to dogs that are uninfected. The change in smell occurs before any physical signs. So asymptomatic dogs smell differently, even though there are no visible physical signs. So just let me see what was my next slide. Okay, so this is the work of Oliveira, and they did some principal component analysis that showed that the infected dogs clustered differently to uninfected dogs when they looked at the amounts and types of chemicals that were produced by infected and uninfected dogs. We did a small study in Governador Valadares, which is a city in the mid-central part of Brazil, state of Minas Gerais. It's on the Rio Doce River, which a few years ago some of you will have read about the mining collapse, not the more recent one, completely contaminated the river with toxic metals. Okay. So what did we do? We collected, so the point of this experiment was we wanted to know if there was a better way of detecting the difference in the smells of infected and uninfected dogs than using GC-MS, gas chromatography coupled to mass spectrometry, which is a brilliant technique if you want to know exactly what the chemical is and you want to quantify it, etc., but it is not a potential diagnostic tool. What we wanted to do was use something called an electronic nose, which it can be very sensitive, but it doesn't give you information on what the difference between infected and uninfected is. It gives an impression of a smell like a human nose. It doesn't tell you what the chemicals are. It just tells you that apples smell different to oranges. And an electronic nose does something similar. It just tells you that two things smell differently. So from the previous work, we knew that infected dogs would smell differently to uninfected dogs, but we wanted to know, would an electronic nose be able to detect that, and could it detect the difference reliably to potentially make it a future diagnostic tool? So we collected small amounts of blood from dogs. We used those blood samples to determine if dogs were infected and what their parasite load for Leishmanian phantom was. We collected blood from 185 dogs in 2017 and 149 in 2018. We also collected a small amount of dog hair. And here's Monica doing her PhD, collecting a little bit of hair, 2 grams, I think it was. And then we took the hair back to the UK and collected the smells from the hair and presented it to the electronic nose. People were concerned that we were defacing their dogs. We were taking clippings of hair, and they said, "You've made my dog look less attractive than it was before," which is very touching, actually. Okay, so this just shows you what samples we took. Okay, so we had some symptomatic dogs, some that had a limited number of symptoms, and others that were fully symptomatic. We have asymptomatic, oligosymptomatic, and symptomatic dogs. This is our eNose. It's a box. It looks a bit like a hi-fi component, the amplifier, if you like. It draws the air inside, passes it over a sensor array. The sensor array is just made up of sensors which are silica coated with a polymer with a current or a voltage across that device. When the chemical from the odor interacts with the sensor, the current flowing through the sensor is modified very, very slightly. And that is what is being recorded. So this is the display from the sensor, from the eNose. All of these colored lines represent each of the different sensors within the sensor array. And there are 12 sensors, and each has a positive and a negative, giving you 24 potential readings. And the computer within the box will tell you the area of the curve for each of those particular sensors, its desorption, absorption, and divergence from 0. And then it constructs, if you like, a profile for each odor that it is being exposed to, so each dog. And to cut a long story short, what we found was that our samples that we collected, for example, in 2017, that the positive dogs grouped very significantly away from the negative dogs. There is a bit of overlap, but the idea is that the eNose can detect the difference between the smells of infected and uninfected dogs. So it's potentially could be a useful diagnostic tool. So the company that we're working with to do this work, they have developed a handheld eNose device, and what we want to now do is use that handheld device in Brazil to see if we still see that difference and if we can improve both our sensitivity and specificity. So our sensitivity and specificity, that's the difference between false positives and false negatives. We had greater than 94%, and in some cases 100% ability to discriminate between the two. And this is in a very early prototype situation. I'm also interested, just very briefly, on the biological significance. If you have an infected dog, that the odor is manipulated by the parasite, that's the implication. What does that mean? So we've been doing some experiments in the lab with our sandfly colonies, and what we find is that the infected dog odor is very attractive to female sandflies. So these are experimental replicates. This is the positive, that's infected dog odor, negative dog odor, so it's still dog odor, but from a dog that's not infected. And we find that the sandflies always go to the infected dog odor. They choose it over the uninfected dog odor. And this is Monica's work. I thought, Monica, you're just trying to please me. You want to give me the results that you think will make me happy. Because they do make me happy, because it's telling me what my female sandflies are doing. So she did them blinded, and not to be epitomised. We took the samples and we hid the identification, and she repeated this set of experiments and got exactly the same results. Interestingly, so that's the female sandfly response. When we attempted it with the males do not differentiate between the infected and the uninfected dogs. It's the females that are making the differentiation. And that is, I think, quite important in terms of the epidemiology of VL transmission in real life. Because an infected dog clearly stands out as infected, and the females, for some reason, and we don't know why, and if anybody can explain why an infected dog should be more attractive than an uninfected dog to a sandfly, what is the benefit to the sandfly? I can understand the benefit to the parasite, but why would an infected dog be more attractive? Unless it's something to do, perhaps, that you get a better blood meal or something. I don't know. There's a lot of work to do. Okay, so that's where we're up to. The ENO's summary: infected and uninfected dogs are not homogeneous. The results that we have, we've had to do some statistical manipulation and so on just to help us. We were a relatively small data set, so we're going to try and do this on a much bigger data set. But we did find very clear differences between infected and uninfected. I'm running out of time. Right, acknowledgements. For the pheromone work, a very big project over a large number of years, about 6, 7, or 8 years. I'd acknowledge Oren Courtney, who's my collaborator and co-applicant in the project to the Wellcome Trust. But all of these other people, all who spent a lot of time and did a lot of work. I can't list them, I can't go through them all. And on the ENO's work, Monica Staniak, my PhD student in Lancaster, Luigi Serra, who's been doing the statistics, Rod Dillon, Christian de Souza in Brazil, Erica Costa, veterinarian, and Tim Gibson at our company that we work with, RoboScientific. So thank you for listening. I'm sorry it was all a bit rushed through, but there we go.
Okay, thank you very much. We have questions. Go for it, Albert.
I was wondering, when you were looking into the efficacy, the efficacy of your attracting the pheromone,
Yeah.
and you were looking into positive or negative for infection, do you use also bite and exposure marker? Because at the end, you just want to know whether the dogs are exposed to the bite regardless of they get infected or not.
Okay, so for the pheromone, we didn't, the xenodiagnosis thing, we did not do that. No, we were simply interested to know if the dog had seroconverted, if it had been exposed, a naive dog that had been exposed to the parasite, and then if it had been, what the parasite load might have been, and so on. So, but we didn't look at how these changes might have affected its attractiveness and so on.
Yeah.
But there wouldn't have been time. We were full of time doing what we were doing.
Okay, I have another quick question. I have to rush to another meeting. But when you looking into the identification of the pheromone,
Yes.
I don't know whether infantum leishmaniasis in dogs leads to an ulcer in first place. Whether you were taking samples close to the ulcer or just any part of the body of the infected dog?
We just took the sample from the hair on the back of the dog, so we weren't trying to take it from near the nose or the ears where there might have been ulcers,
Okay.
or in other places. It was only from the hair, and the best place to get 2 grams of hair, which is quite a lot, was from the dorsal surface.
It comes from a comment from Valenzuela telling me that he's convinced that the sandfly looks for where the ulcer is for a bite, which will maximize transmission back to the sandfly.
Okay.
So maybe there might be a higher concentration of the molecules you're looking for, and maybe even bacteria in the ulcer could also be working as an attractant.
Well, that's very interesting. And of course, we were taking blood, venal blood, which is not a very good marker for infection. We should have been, as it turns out, been taking skin samples from ears, where dogs that are infected have very high levels of parasites in the ears. And we will remedy that if we get the funding to do the next thing and address that issue that you're making. But not all of these dogs are symptomatic. Only about half of them are symptomatic, so they had no symptoms whatsoever, no ulcers, nothing. And that's why it's quite exciting, because if we can identify asymptomatic but infected, and I know that's different to infectious, but that would be a step forward. And the test can be done in about 5 minutes, not 2 weeks or longer.
Okay. Yes. Charles. We'll go quickly.
Just to know whether this approach could be applied beyond South America, in India, in Africa, could you use the pheromone approach to also?
Well, yes, in principle. The drawback for the pheromone control approach is that we don't know if Argentipes has a pheromone. There is some evidence, behavioral evidence, that others have collected and that we have collected, that there is a pheromone that is operating in Argentipes, for example, but we don't know what it is. If we found it, yes, of course, I think it's an aggregation pheromone, and there's evidence that Argentipes aggregate. If that aggregation is driven by pheromone, then we could manipulate in that way. Yeah.
Okay, thank you very much. Now, there is a class in here afterwards, so we're going to have to wrap up there, I'm afraid.
Sorry.
But thank you very much, Gordon. Very great.